Welcome to Lecture 18 of Networks, Friends, Money, and Bytes. And today's question is, why is Wi-Fi faster at my home than at hotspots? And this might be a question that many of us are wondering about. And the root cause in 2 bullets is that the interference management system used in Wi-Fi does not scale well as the number of stations or user devices increases, even from just several to, say, 10 or a dozen. In other words, the tragedy of the commons, which we observed in many different social and tech networks, is not efficiently mitigated in the case of Wi-Fi by what they use as the random access method, as soon as the crowd is reasonably big, for example, in a hotspot, and increasingly perhaps at home as the number of Wi-Fi devices active at the same time increases at home too. In order to get into the more complete answer, we have to look at a little bit of the history of Wi-Fi. Okay. Now, Wi-Fi started in the mid to late 90s in the standardization body by IEEE. Now, you have seen quite a few different standardization bodies names, such as IETF, mostly for internet type of standards. You've seen ITU, and you've seen in cellular world so-called third generation standardization body 3GPP and 3GPP2, and indeed there are quite a few other standardization bodies such as MPAG, such as DSL Forum, WiMAX Forum. Some of them are less restrictive than others in terms of the standards that they issue. Now, IEEE is the one that's responsible for a lot of local area networks. In a homework problem back in Lecture 13, we looked at a wireline local area network, the Ethernet, okay, and the switching method over there for detecting a spanning tree distributedly. Now, Wi-Fi is really a wireless version of a local area network. So sometimes it's also called a wireless LAN. Okay? And then as the first and then second generation of cellular standards took off, people in the community wondered maybe we can invent another complementary type of wireless systems. Now, today, there are billions of Wi-Fi devices and hundreds of millions are added every year around the world. And they are used at home for Wi-Fi connectivity. Imagine the number of wires you have to put together in your home if you didn't have Wi-Fi. It's used in office extensively, and it's also used in public hotspots, which could be hotel, airport, coffee shop, and so on. Now, similar to a cellular network, Wi-Fi also used a fixed architecture. We'll see in a picture soon that there is something like a base station called access points. Okay? And they are connected among themselves by some kind of wires. But there are also crucial differences between Wi-Fi and cellular. For example, in Wi-Fi, the range of communication is much shorter, and the allowed transmission power is also smaller. So this short range is something around, say, 100 meters. There's little mobility support. If you move between, say, 2 access points controlled by the same controller, maybe that's okay. But in general, as soon as you move away from one Wi-Fi AP access point, then you lose connectivity. You have to reassociate again, and the session may drop. But the biggest difference might be the underlying physical media. In cellular, what they use is licensed spectrum. Okay, you have to pay billions of dollars to the government to acquire the right to transmit in that frequency range. But for Wi-Fi, they use so-called unlicensed spectrum. Okay. There are quite a few different unlicensed spectrum. One is the so-called ISM band, industrial, science, and medical frequency. Okay. And there's one in the so-called S band, and that is around 2.4 gigahertz, and the other in the so-called C band around 5.8 gigahertz. All these are unlicensed, meaning that you do not have to pay the government or anybody any money. You can just go ahead and use it. Now, in fact, in the 2.4 gig, which is where Wi-Fi started in the 90s, the dominant usage before Wi-Fi was actually microwave. Okay. Good thing that you don't have to pay government money in order to microwave popcorns. And then Wi-Fi community said that, you know what, let's use these two bands of unlicensed spectrum, starting with 2.4 gig. So here is a typical topology of a Wi-Fi deployment in your home, hotspot, and so on. As I mentioned, there is something called access point AP. This is similar to a base station DS back in lecture 1. So this is lecture 18, and we've come a long way. Now we're back to the wireless world. And then there are a lot of end-user devices. Almost all devices have a Wi-Fi connection today: laptop, desktop, TV, games console, of course your phone, your tablet. And they communicate wirelessly, denoted by these dotted lines, to the access point. Now, how do they find the right access point to talk to? That is one question we'll answer later. And this is called a basic service net, BSS. Okay. And a bunch of BSS can form what's called extended service net, ESS. And these APs are then connected among themselves through some wires, for example, Ethernet, and then tapped into the access network, which then further gets into the cloud, into the rest of the internet. So this is similar to a base station and a mobile station. And a base station is sometimes called Node B or evolvable eNode B in different generations of cellular. Okay, but the idea is that there's a one-hop wireless followed by wireline access. However, as we mentioned, that spectrum is unlicensed, range is short, and mobility support is limited. And this is the underlying spectrum around the 2.4 gig. There's slight difference in the way the channels are decided in chopping up the frequency bands across different countries. In the US, here is the typical picture. Okay, you got 11 channels, 1, 2, 6, up to 11. Okay, the middle channel 6 is centered around 2.437 gigahertz, and the width of this channel is 22 megahertz with a little guard band of 5 megahertz on the side. Okay, so I should say this is not joined to scale. Okay, you can imagine 3, 4, 5, and so on and so forth in between. Okay. So as you can see that a lot of these channels actually overlap. Okay, with signal processing's help, you can take care of some of that overlap. But if you want truly orthogonal frequency bands, then you actually need to say, I can only use channels 1, 6, and 11. These are the three channels that are truly non-overlapping in the frequency band. Okay, so there are 11 channels, but 3 that are truly orthogonal. Now, the question we're going to try to address first are the following. Okay, terminology-wise, is Wi-Fi the same as 802.11? Yes. So 802.11 is the IEEE standardization body, okay, for local area network, and Wi-Fi is just a much sharper name. Wireless Fidelity is the original name. Now, very few people remember that. They just call that Wi-Fi now. So imagine if you call your home connectivity IEEE 802.11. You know, that's not as attractive as to say, hey, we got a Wi-Fi here. But what about this business of 11A and B and G and N and E and H and R? And sounds like a very lazy way to do alphabet soup. Okay. Well, these are just different subclasses of the 11 family. It started actually with B. Well, of course, they tried to start with A first, but the standardization around family B actually gelled before that of A. So 11B back in 1998, for example, that was the only family available if you want to buy a Wi-Fi product. Okay. And this used 2.4 gig, and it can give you a reasonable data rate up to 111 megabit per second, up to. Okay, we'll see that when the interference is strong, then you can go all the way down to 1 megabit per second. But in 1998, 11 in the best case was already pretty impressive. And then came along G, which still uses 2.4 gig, but with more advanced signal processing can give you up to 54 megabit per second. Again, up to 54. And then A finally came along. It also can achieve 54 megabit per second, but it uses a different spectrum, the 5.8 gigahertz range. Okay, so the radio analog front end requires a different kind of chips. So A, B, G were sort of the dominant three variants in the mid-2000s and so. In the last several years, there's the proliferation of .11n, and now we use even more fancy signal processing, including something called multiple input, multiple output. It's really multiple antennas at both the access point, say 2, as well as your device, say 2. In next lecture, 819, we'll talk a little bit about the throughput implication of using the MIMO devices. Together with earlier advances such as so-called OFDM, orthogonal frequency division multiplexing. Okay, this is not a wireless signal processing class, so we won't go into that detail. But together with all these techniques, people are able to take the speed from the max of 54 all the way to, say, around 300 megabit per second. Okay. Again, up to, but typically you can observe something around 100 megabit per second, maybe half of that, but still, that's very impressive. In fact, if you look at, in many cases, the wired backbone of the Wi-Fi network, they don't have more than, say, 50 megabit per second. So the air interface is already not the weakest link anymore as soon as .11n is used. So now people are talking about using .11n as a way to do very high-speed transmission within the home, even for transmitting HD TV signals. And then there are other kinds of letters associated with .11 family. Okay, and these are not different throughput classes anymore, but are mean different kinds of enhancement of the .11n family. For example, E and H and R, they give you better quality of service, they give you better security and better roaming or mobility support. Now, there are many interesting stories about Wi-Fi in recent days. For example, when Steve Jobs announced iPhone 4 a couple of years ago, he couldn't get on the Wi-Fi network inside the auditorium. So he had to ask everybody else, please get off the Wi-Fi, and then he was able to get on the Wi-Fi. In 2011 summer, the Korean government announced that the city of Seoul will be blanketed by Wi-Fi around year 2015. Okay, so every street corner will be provided with a Wi-Fi capability. And then now, as I mentioned, a lot of manufacturers and service providers are talking about getting rid of the wire. So from the residential gateway all the way to the HD quality set-top box on your TV using Wi-Fi. Now, you may have also seen quite a few annoying things about Wi-Fi. One is that you cannot get on. Sometimes you know why you can't, because there's a lock, okay, and you don't have the passcode. Sometimes there's no lock, but somehow you can get on. Part of that is because of the backbone issues. For example, backbone might be congested, or there usually is a so-called DHCP server that can rent you an IP address for a period of time. And without IP address, you can't do much. So we'll talk briefly about this in lecture 13 and more in the next lecture. Sometimes you say that, hey, I can get on the Wi-Fi, but the performance is very poor. Poor performance, very low throughput. For example, on the train, okay, like Amtrak in the US, they announced a couple of years ago they'll provide onboard Wi-Fi. I tried many times. Either I can get on or get on and get 50 kilobits per second. So where is my whatever 100 megabit per second? Where's my 10? Where's my 1? Where's my 0.1 megabit per second? Well, I was getting such a low speed I really cannot use it. Sometimes you see that, hey, just at certain time of the day, for example 8 p.m. on every weekday, suddenly it doesn't work very well. Now again, part of that could be backbone congestion, but part of that could be your neighbors, especially living in a high-rise building, turn on their Wi-Fi as they get back home. Now a lot of homes have something like 10 or so Wi-Fi devices. If they're all active, then you see a lot of interference. So our question is, how can we understand and tackle a lot of these performance issues? Now part of the problems stem from the fact that Wi-Fi has very limited radio planning. By planning, I mean radio planning. Okay, first of all, it's unlicensed band, so it is just hard to plan. Okay, anybody can stick an AP over there. It could be a service provider, it could be your neighbor. You can't really control that. Okay, so people say, I'm just give up trying to plan. Instead of doing that, I'll just say, you know, let's just open up a box and do it. Now compare that to cellular world. The spectrum is very expensive. You need to have the legal right to transmit over there, and the equipment is also much more expensive. It's not $50 box of AP. So it is tightly controlled by the cellular providers, and they do very careful radio planning. Where and how do you put the antenna together? Okay. Second is that there's very light management. Unlike the internet or the telephone cable world, where there's a lot of network management going on traditionally within the network, there's very light management going on for Wi-Fi. Okay, very little stable tools for root cause analysis, and very few signaling channel on the control plane to control and adapt the Wi-Fi's. But the situation might be changing over the next few years. The backhaul might be the bottleneck, either because the DHCP server doesn't give you an IP address. For example, certain campus networks banned on iPhone because their DHCP server has a bug relating to iPhone. Once you give you an IP address, it won't be able to get it back. Okay, so they say, all right, no more iPhone on our Wi-Fi. Sometimes it's because of the air interface, because of interference, for example. And that is the heart of this lecture. So what are the degrees of freedom that you can use to tackle these problems? Well, starting with the first order one, which is find the right access point to associate this Wi-Fi device with. Part of that is carried out by sending a beaconing signal and comparing the kind of signal strength that you can get from different APs. Then you have to select the right channel. Okay, we mentioned, for example, in .11b, okay, there are only 3 truly orthogonal channels. That's 1, 6, and 11. Now, unfortunately, most enterprise or residential customers, they just open up a box, and the default channel by the manufacturer, say, you know, Linksys, would say that it's all channel 6 for this batch of APs. Then right there, you've got many APs transmitting in the same channel, even though they could spread themselves around to different channels. But many residential and quite a few percentage of the enterprise customers simply do not adjust that. And then there's the rate selection. Okay, for example, should I transmit at 1 megabit per second or 11 megabit per second, and somewhere in between? So the question, this question depends on what kind of interference condition are you experiencing. Sometimes you try to be too aggressive, sending a too high rate, even though the medium is bad. For example, in a noisy cocktail, if you talk too much, like what I'm doing right now, then the other end may not hear you clearly. You say, well, bad channel, let me talk very slow, and maybe louder as well, right? Let's say you get the right AP, you do some smart channel array selection. Then what? Then is the problem of collision. Okay, collision of frames. And this will be picked up in the next module of the video.